One page of your Earth Science reference table, you have this chart that shows you radioactive decay data. And it gives you 4 different isotopes, which are radioactive. It shows you what they disintegrate or decay into. And then they give you something called the half-life, which we'll look at in a minute. Actually, let's look at that now. When these radioactive elements decay, the decay happens at a certain rate, certain speed. The time that it takes for half of the atoms to decay is called the half-life. So let's say that an animal just died, and the animal has carbon-14 in it. The moment that it dies, all the carbon-14 is still there. 100% of it is there. Nothing has decayed yet. After one half-life, half of the parent material will decay. So now there's only 50% of the parent left, and the part that decayed turned into the daughter. When we add them up, we still will have 100%. After a second half-life, we're going to lose another half of the parent. So now there's 25% left of the parent and 75% of the daughter. It still equals 100%. After a third half-life, we're going to lose another half of the parent. So now we only have 12.5% of that parent material left. The rest has decayed into the daughter. And we could keep going, a fourth half-life, a fifth half-life, and so on. We just keep taking away half of what's left of the parent. When you graph this, your graph will always look like this. It doesn't matter which of the isotopes we're talking about. At your 0 half-life mark, you're always going to have 100% of the parent. After your first half-life, you will have 50% of the parent and 50% of the daughter. At your second half-life, you lost half of the parent, so the 50 drops down to 25. At your third half-life, we lose half of the 25. We drop down to 12.5, and so on and so forth. Now, if you're thinking this through, you hopefully realize that if we keep taking away half, we're never going to get to 0. Because if you take away a half and a half and a half and a half, you'll never reach 0. So the parent material will never completely decay, and the daughter material will never reach 100%. Now, every isotope has its own unique half-life. Carbon-14 takes 5.7 times 10 to the third years, or 5,700 years for half of it to decay. Potassium-40 has a much longer half-life. It takes 1.3 billion years for half of the potassium to decay. Uranium, 4.5 billion years. Rubidium-87, 49 billion years, a huge amount of time. What's key about these half-lives is that half-lives never ever change. Carbon-14 will always take 5,700 years to go through a half-life. It doesn't matter what you do to it. You can heat it, you can cool it, you can crush it, you can cut it in half. It doesn't matter what you do. The half-life will always stay the same. And that is the key to using this process. So let's look at a couple of practice questions. Okay, question 1. An ancient bone was found and analyzed and found to contain carbon-14 that had decayed for nearly 2 half-lives. They want to know how old the bone is. Okay, well, we know that 1 half-life for carbon is 5,700 years. So if it has gone through 2 half-lives, it means it went through that 2 times. So 5,700 times 2 is going to equal 11,400 years. Okay, let's look at a second problem. An igneous rock contains 1/2 of its original amount of potassium-40. How old is the rock? Okay, so they're telling us that this rock contains 1/2 of what it originally had. So we're going to refer back to that chart that we looked at before. This chart will help you with any of these questions. My advice is to always draw this out on your paper and then use it for as many questions as you need to. Okay, so the rock has 50% of its potassium-40. So we know we started off with 100%, and if I'm left with 50%, that means it only went through one half-life. So for potassium-40, one half-life is 1.3 billion years. So that's how old this rock would be. Let's look at another one. After 11,400 years, how much carbon-14 would remain in a fossil? Okay, so now they're giving us a longer amount of time, and we have to determine when this fossil died and how much carbon-14 would be remaining. So we know that the half-life for carbon-14 is 5,700 years. That's how long it takes for half of the carbon to decay. We have to figure out how many half-lives would go into this total amount of time. So it turns out for this problem that if you multiply 5,700 by 2, you will get 11,400. So this is going to be equal to 2 half-lives. So again, we're going to want to use that same chart. So we started with 100%. After the first half-life, we're down to 50. After the second half-life, we're down to 25. So the answer for this question is there'd be 25% of the carbon-14 left. All right, question 4. If radioactive material were cut into pieces, what would the half-life of each piece be? So do you remember what we talked about before? Right, half-life never changes. It doesn't matter if you cut it into pieces. It's going to be the same. Okay, let's look at 2 more questions. So what is the approximate age of an igneous rock that contains only 1/4 of its original potassium-40? So there's only 1/4 of it remaining. So that's the key to figuring this out. So again, I need that chart. Well, if there's only 1/4 left, that means it went through 2 half-lives, because 2 half-lives gets you to a 1/4. We're dealing with potassium-40, so 1 half-life is 1.3 billion years. Now we said it had to go through 2 half-lives. So we're going to simply multiply this by 2, and that will give us 2.6 billion years. That's the age of this rock. And for the last practice question, a sample of wood found in an ancient tomb contains 25% of its original carbon-14. What is the approximate age of this wood sample? Okay, so it has 25%. So I come back up to this chart. So 25% again, that's 2 half-lives. Well, I know for carbon-14, each half-life is 5,700 years. If there have been 2 half-lives, it means this piece of wood is 11,400 years old. Okay, so those were some practice questions. We'll be doing many more in class. Now, there are some other things that you need to be aware of when we're using this process. First of all, if you want to use this technique, you have to figure out which element to use. If an element has a short half-life, it means that it breaks apart quickly. And so after a short amount of time, it will have broken apart so much, it's going to be really hard to measure. There's going to be so little of it left. For example, out of the isotopes we've been looking at, carbon-14 has the shortest half-life, right? 5,700 years for half of it to decay. After around 70,000 years, there's not going to be enough carbon left to even measure. So you can only use carbon-14 for things that are not very old. If you want to date something that is very old, then you want to choose an element that has a long half-life. For example, uranium-238 has a half-life of 4.5 billion years. That means if you have a rock that formed 1,000 years ago, you would not be able to use uranium-238 because it did not go through any half-lives yet, right? It takes 4.5 billion years to go through one half-life. So the rock would have to be older than 4.5 billion years old in order to use the uranium, okay? So you have to think about whether you want an element with a short half-life or a long half-life. The other thing you need to think about is whether your element will be in the object that you're trying to date. All living things have carbon-14. Rocks don't. So if you're trying to find the age of a rock, you would not want to use carbon-14 because the rock doesn't have any of it. Same thing with uranium-238. That one is found in rocks, but it's not in living things. So if you have a fossil, uranium-238 is not going to help you. So you have to know what elements are in each object. So I hope this video helps you make a little bit of sense with radioactive dating. Come on in and see me if you have any questions, and we can do a lot of practice together.